Good evening. Tonight we welcome our speaker, Dr. Tom Joshi-Hartley, a graduate from the University of Exeter, and his thesis focused on computational models of convection in stellar interiors. He can be found when he's not running simulations on a computer. He can be found playing cricket, netball, or giving talks on astronomy. So let's give a big welcome to Tom Joshi-Hartley. Thank you very much.
Hi. Yes, thank you. Thanks for that introduction. I'll just quickly share my screen. So hi, I'm Tom Joshi-Hartley. I've just finished up my PhD at the University of Exeter, and as you mentioned, that was on simulations of convection in stellar interiors. I've been looking at specifically how the efficiency of heat transport is affected by the rotation and the magnetic fields in a star, how fast the star is rotating and how magnetic it is. In this talk, I'm going to talk you through a little bit of, so I'm going to start off by talking about energy transport in a star, the different ways that energy is transported within a star. And for the most part here, energy just means heat. So talking about how heat that's generated in the core makes its way to the surface of the star. I'm going to talk you through kind of the sun from the inside out. So we're going to start with a little bit of how it formed, and then we're going to start at the core and work our way outwards, describing what the different regions of the sun are like. And particularly when I get to the stellar surface, we'll talk a little bit about some of the observable elements of the solar surface and what drives those, where those come from. I'll briefly discuss the solar cycle and magnetic fields that happen in the sun, and talk about how things are different for other stars. This is definitely a focus on solar-like stars rather than your low or high mass stars. But I'll cover those a little bit as well. Once I've finished with this section, I'll then talk you through a little bit of stellar life cycles, how stars evolve and how that's different for high and low mass stars. I'm hoping you can still see everything there. My screen's just jittered, but hopefully it's all back to normal for you. Maybe if I could just get a thumbs up from the front row or something so I can see if it's still working. Yeah, great. Okay, wonderful. So we'll crack on then. So let's talk about the three methods of heat transport. So imagine you've got a gas hob, and you're trying to boil some water for pasta. First thing is you light the hob, and if you hold your hand above that, you can feel some heat coming off of your gas fire. So some of that heat is going to be carried by electromagnetic radiation. So you can see the fire. It's blue or it's orange, depending on how much oxygen it's getting, and you're seeing it because it's emitting photons, both in visible light, which is what's letting you see the fire. But it's also giving off photons in infrared light, which is essentially heat radiation. So if you hear somebody talking about radiative transport of heat, that's what they're talking about, heat carried by electromagnetic radiation. And that's where something is if you've got a fire in your front room and your coals are glowing hot, they're going to be radiating out these infrared photons, and transporting heat in that way. But it's not super efficient radiative transfer. If you wanted to cook something based solely on radiative transfer, you'd be waiting a long time. But luckily, if we put a saucepan of water on our hob, only the bottom of the pan is actually next to the flames. But over time, you'll find if you waited long enough that your whole pan, including the handle, which is far away from the flames, would heat up. And this is because the heat is carried through the metal by vibrations of the atoms that make up the pan. So as you heat the vibrations, as you heat the atoms, they get more energetic, they vibrate a little bit faster, they'll knock into their neighbors and carry that energy through the metal. And this is conduction. This is the transfer of heat through vibrating atoms. Probably conduction is a method of heat transfer that you're quite familiar with, and you've probably heard of the next one as well, of convection. So if you put some water in your pan, after a while, the water in your pan will start to boil. But how is that heat getting transferred through the water? Water's a fluid, so the atoms in the water are more spaced out, they're more spread apart. So giving one atom more energy doesn't immediately transfer that energy to its neighbors, and you need to give it a lot more before it can. In fact, water is quite a good insulator for exactly this reason. So conduction isn't going to help us here. So what we rely on inside a pan of water is convection. So convection is a little bit trickier to understand. But if we imagine a kind of blob of water towards the bottom of our pan, close to that metal surface, which is heated by conduction, some of that heat will get conducted through into the water and will allow that blob of water that we're going to imagine, this blob of fluid in the bottom of our pan here, it's going to allow that to heat up. And as it heats up, it's going to expand. That expansion means the density of this blob of water is now less than its surroundings. So our blob is less dense, and you might have heard that hot fluids rise. This is something that's often said about heat and air. If you live at the top of a block of flats, you don't need to put your heating on as much because everyone underneath you has turned on their heating and their heat has risen up through the building and your flat's nice and toasty, which that happens for me. I live on the top floor and it's a little frustrating sometimes because it ends up a bit too hot. And even if we've not got our heating on, there's nothing we can do about it because everyone else has got theirs on. But that concept, that hot fluids rise, that counts in water as well. So this hot, less dense patch of water is going to rise up towards the top of our pan. As it's risen, it's now hotter than its surroundings, and so it's going to let go of some of that energy. It's going to let that dissipate into the surrounding water, so our blob is going to cool, and the surrounding water is going to get a little bit hotter. As that blob of water was rising, it couldn't just leave a gap in the bottom of the water. That's not the way fluid works. Something is going to have moved in to fill the place, making some fluid motions start to begin. And in fact, if we say that bit of water that's taken its place has moved from the right-hand side of the pan here, then now we've got a gap here, and our newly cooled blob of water is going to move through into that space and eventually be brought right back down to the bottom of the pan where it can get heated again, and the whole process can continue. And over time, this means that your ambient temperature of your water, your average temperature, is going to increase. This is the essence of convection. Convection is the heat transport by the movement of hot material, and you kind of form these cycles of hot material rising and cold material falling. That can happen over time to transfer your heat upwards and to raise the temperature of your water in this case. So the quick wrap up there is that radiation is the heat transfer through photons being emitted. Conduction is heat transfer through vibrating atoms, and convection is heat transfer through movement of warm material. So now that our little mini science lesson is done, a little recap, we'll move on to the astrophysics. So how did our sun form? Well, essentially, 4.6 billion years ago, we have some cloud of dust and gas, which exists in the interstellar medium. And let's say that one point is going to be slightly hotter and slightly denser than its surroundings. And we'll call that this middle point here. Because that bit's a little bit more dense than everything else, it's going to have more gravitational attraction, and it's going to pull its surroundings in towards it, as we see in this simulation. I like this simulation. This is from a simulation done by somebody that works at Exeter. It was published in 1998. The reason I like this simulation is because no matter what audience I'm talking to, I get a good reaction from that date of 1998 when I say that that's the same year I was born. When it's astronomical societies like this, that prompts a lot of rolling of the eyes, achy groans perhaps. When I'm talking to school children, that prompts a load of, whoa, you're so old. So no matter what audience I'm talking to, it gets a good response. But the essence here is that as this cloud of dust and gas contracts, and we'll watch that movie happen again, it gets hotter and denser in the middle. And eventually that central region will get hot enough and dense enough that our protons that are floating around in that gas can combine and cause nuclear fusion, and you get a star. And that's when this video ends. This simulation ends when nuclear burning begins. And you can see that you're left with this kind of gas, these spiral arms. It might look a little bit like a galaxy. This is a protoplanetary disk, which is a whole region of astrophysics looking at these disks, because it's in these disks that our planets form. The remnants of the dust and gas and rock that's left in these disks form your gas giants, and then later on they form your rocky planets. The exact processes through which these planets are formed, they're actually not super well understood, which is why it's such an ongoing region of study. It's not my area, so I won't spend any more time on it. And we'll move on to talking about the sun. But for all stars, including our sun, this is the way that they form, through this collapse of dust and gas. So moving on to talking about the sun again, we've got our sun here. and the sun contains around 99.86% of all of the mass in the solar system. I think it's an important thing to try and get across that the sun is really big, and everyone kind of knows that, but I think trying to get across just how big the sun is, it can be a little tricky sometimes. So I've got both the mass here, 99.86%. Essentially, the solar system is just the sun. Everything else is a rounding error. If we then look at that 99.86, Jupiter on its own is then 0.1%. So all the other planets are just 0.04%. So the vast majority of everything is the sun, and then there's Jupiter, and then there's everything else. And the planets in this image in front of the sun here are to scale. So the sun is a lot bigger than all of the planets. The sun is 72% hydrogen, 26% helium, 2% carbon and oxygen, and then there's not a lot of much else in there. There's a little bit of what astronomers just called metals, which is things heavier than helium, but predominantly it's hydrogen and helium. Sometimes people think that helium is there from hydrogen burning. Hydrogen burning will convert hydrogen into helium, but most of this helium is left over from the Big Bang. It's not been produced internally in the sun. Every second, the sun converts 600 million tons of hydrogen into helium. And because I really like a meaningless comparison, 600 million tons, I think that's a really big number. How can we conceptualize that? Well, it's 1.2 million Boeing 747s. I'm not sure that's any more useful, but if you're really intimately familiar with the weight of a Boeing 747, well, imagine 1.2 million of them. And then another meaningless stat, because I like them so much, the sun produces 3.8 times 10 to the 26 joules of energy every second. This is the equivalent of boiling 100,000 trillion kettles. How big is 100,000 trillion? I think that's not really something worth spending much time on, but it's a good little fact. Okay, so what about the interior makeup of the sun? What does it look like inside? So we've mentioned already that this hydrogen burning occurs in the core. We've got the core in the middle there. It's about the inner quarter of the sun. And then I talked about different methods of heat transfer earlier on. And that's how we actually split up the regions of the sun. So neighboring the core, we have the radiative zone, where heat is transported through radiation. And actually, a lot of the fluid is very static and stably stratified. We then have this convective region towards the outside of the sun that makes up the remainder. In this area, the heat is transported through convection, and the plasma itself is moving. And so it's a much more dynamic region. As we get to the surface of the sun, we have the photosphere, which is what you think of as the visible surface of the sun. You've got your chromosphere, which is the region through which you get things like prominences, things that eject off of the sun, and then your corona extends out much, much further, and that's your kind of solar atmosphere, charged solar particles. And we'll talk about these one by one from the inside out in a little bit more detail now. So starting with, before I do that, the last couple of things you can see on this diagram that I'll discuss later on, sunspots. We can see these dark patches on the sun, which are consistent with observations, particularly at what we call solar maximum, which I'll talk about a bit more later on, and prominences, which are these big filament-like structures that come off of the surface of the sun. And I'll talk a little bit about how these things form. So starting at the core and working our way out, the solar core makes up the inner quarter of the radius of the sun, about 174,000 kilometers, and it's the hottest region. It's at 15 million degrees Celsius. Because it's so hot, nuclear fusion can occur here, which generates all the heat and energy of the sun through this conversion of hydrogen into helium. This process happens through the proton-proton chain. And I've got a little animation here of some of the steps of this process that we'll go through in detail while it loops. So we start off with two hydrogen nuclei, basically just two protons, which are just there in the core. And over time, these will collide together and they'll merge. They'll form a positron, an electron neutrino, and some deuterium, which is like heavy hydrogen. It's hydrogen with a kind of an atomic mass of 2. When we form that deuterium, like that step now, that can collide with another one of these protons floating around, another hydrogen nucleus, to form helium-3 and also a gamma photon, a gamma ray. The gamma ray I'll come back to in a moment. The helium-3, that's not super stable. That's not going to exist for a long time. But luckily, there's a lot of them floating around because this is happening a lot. If that helium-3 collides with another helium-3, it'll form helium-4. As well as 2 more protons, which are released out to continue this chain. So what we've essentially got here is we've got three hydrogens coming together to form helium-3, and two of those collide to form helium-4 and two hydrogens. So you can see that it's kind of six protons create a helium-4 and two protons. So it's a process that over time will run out of fuel. You're ending up with less protons than you started with, and so you're going to convert that hydrogen slowly into helium-4. But because this process also produces protons, it's able to keep going for a little bit. This positron, this like a positive electron that was formed in the first step, this can collide with an electron that's floating around in the core. They can annihilate and form two gamma rays. So we're also forming three gamma ray photons here as well. And those gamma ray photons are important because they are going to transport us some heat through our radiative zone. So if we move out a little further, we get to our radiative zone, which goes from about a quarter of the radius to about 70%. So it's quite a wide region, 300,000 kilometers, and it's a little bit cooler at a nice balmy 7 million degrees Celsius. So what we can see here, if our animation plays, is the squiggle in this diagram represents the photon, our gamma ray photon. And it's not playing particularly smoothly, but hopefully you can see that the photon travels until it hits a proton. This is still quite dense material. The protons are packed very densely, so a gamma ray photon doesn't have to travel very far before it hits a proton. When it hits a proton, it's absorbed, and then that energy will be re-emitted again with slightly less energy. And less energy means a longer wavelength. So the wavelength of this photon will increase, its energy will decrease, and it will move down the spectrum from these gamma rays that it was emitted as, down the spectrum towards visible light and towards infrared radiation as well. This process, even though the photons travel at the speed of light, they're crashing into protons so often, so frequently are they being absorbed and re-emitted, that if you could kind of tag a gamma ray photon at the beginning of its journey and follow it all the way through, it would take that photon 170,000 years to get from the core of the sun to the edge of the radiative zone. So they're really trapped in there for a very long time as they wait to escape, as they're absorbed and re-emitted. So moving on again to our outer region, our convective zone. This is a very simple model just of convection, setting up a temperature gradient and allowing it to evolve to start to convect. It's not supposed to be like the solar convective zone. That's much more turbulent than this. But here we can see these kind of hot upflows through the middle and the cold downflows down at the sides, and the way that you get multiple plumes that form and set up to carry your temperature gradient. And this is a kind of a very simple simulation. For a more complicated simulation of a stellar convection zone, we can look at this, where now we can see that it's a bit more turbulent and it's less easy to make out an individual plume. But what you can see is this part, that's the solar surface-like element here, the top of your convection zone, has got a mottled pattern, which those of you that have done some solar observing, that might be a little familiar. For those of you that it's not, I ask you to keep it in your mind, this mottled pattern that you can see. And this is the region of stars that my research and people in my research group tend to focus on. We're interested in the convection zone and how convection can transport heat in the stars. Okay, so we now move on to the solar surface. So the photosphere is this visible surface of the sun, which is where we see this granulation. This is a video of the solar surface taken with the Swedish Solar Telescope from May 2017, and we can see this mottled surface similar to what we just saw in the simulation. So what you're seeing here is the dark kind of edge regions. We call this granulation, solar granulation. And these dark regions that kind of join the cells, these are the downflows. The downflows are cooler, so they look a little bit darker, and the bright regions are your upflows. And so you can see the imprint of convection on the solar surface. Each of these cells is driven by convection. And if you're wondering how big a granule like this is, that's the size of the Earth relative to this image. So these things are pretty big. It's also the solar photosphere where we see sunspots, which look something like this. This again is with the Swedish Solar Telescope, and we can see that granulation towards the edge of the image, and then we can see how you've got this dark region and an outer penumbra. So these sunspots are caused where strong magnetic fields penetrate through the surface of the sun, and they basically hold the fluid in place and stop it from convecting, which means the material at the surface in the middle of the magnetic field cools down. It radiates away its energy into space, and it gets colder than its surroundings, and it's not able to be replaced by upflowing hot material. because it's darker, because it's cooler, it gets darker, and so it looks like this a dark spot on the surface of the sun. It makes it appear black. And since radiation, again, here's the Earth for scale to one of these sunspots, that they're pretty big things. Since radiation follows scales like temperature to the power of 4, you only need a slight change in temperature to result in quite a large change in radiation, making something look dark. If the surface of the sun was 5,700 degrees, which it roughly is, a sunspot temperature of just 150 degrees lower would result in a 10% drop of radiation intensity. So a really massive change with just a small change in temperature. In reality, sunspots are about tens of degrees, tens to the most 100 degrees cooler than their surroundings. So when you're seeing these sunspots, you're seeing magnetic fields, essentially, the imprint of a magnetic field. Okay, so as we then move away from the surface of the sun towards the solar atmosphere, we've got the chromosphere. This is footage from the Solar Dynamics Observatory taken yesterday of the sun. So you did your observing last week. I got my video even more recently than that. What I love about the Solar Dynamics Observatory is they do a video, they upload their day's recordings every day, basically. So you can always look at the last 24 hours, and they've got an archive going back a really long way. So what we're looking at here is a chromosphere. This is you can see kind of these bright regions where material is bursting off of the surface of the sun. And it always seems to follow these kind of almost well-defined pathways. You can see maybe there's a region here where you've got a nice clear loop. And so what causes these loops that are known as prominences? Well, if we picture a star that's got a magnetic field from pole to pole like this, which we call a poloidal field. And then we know that the sun rotates, and we know that it doesn't rotate uniformly like a solid body. The equator rotates faster than the poles. So our equator rotates on about a 25-day period. The poles closer to a 31-day period. And this is something that you can check observationally. If you can track a sunspot across the surface of the sun by taking repeated observations through a solar telescope, you can see that different latitudes will rotate at different speeds. And as this differential rotation kind of pulls the magnetic field lines with it, they're frozen into the fluid and they move with the plasma in the solar interior. And it causes these magnetic field lines to become distorted and stretched. As they continue to be distorted and stretched, they twist into loops, which break through out of the surface, and you get these pinched loops of magnetic field. And when these loops form, they release a lot of energy, which generates these explosive solar flares and coronal mass ejections. And we'll look at some of these in more detail. Here's one from 2018. So if we'll get a big explosion of material that bursts out from the sun, and you can kind of see that as it falls back down onto the surface, it follows these loop patterns because there's enough charged material in the plasma that all of the plasma will follow these magnetic field lines. Similarly, the prominences happen when these loops are a little bit more well-defined and last for a bit longer. We've got a video here from 2014 of a really nice prominence. This one, you can see the loop structure, one here, really well-defined. And the material following these magnetic field lines. So we know that magnetic fields are super important in the sun. If we then take another step out, the last part, our solar atmosphere, so to speak, the solar corona, which extends out to 18 times, 19 times the radius of the sun. So the corona is massively extended away from the surface of the sun. It's actually hotter than the surface of the sun. The surface of the sun is about 5,700 Celsius. The corona gets up to 1,000,000 Celsius. And the methods of coronal heating are very much subject to debate. The way that the heat kind of increases again at out into the corona is not totally understood, and there's a lot of competing theories about that. Usually, the corona can't be seen because it's not as bright as the sun, and the sun's light usually blocks out all the light. But if you're lucky enough to see a total eclipse of the sun, like this one here, then you can see how you've got, once the sun is blocked out and you've just got the dark region of the moon in front of the sun here, suddenly the corona comes into view. Sometimes people think of this as just glare around the edge of the sun. What you're actually seeing is the corona itself emitting light, and the light just isn't swamped. It isn't kind of swamped out by the brightness of the solar surface itself. So it's one of the cool things about a solar eclipse. One of the many cool things about solar eclipse is it allows you to get observations of the solar corona itself. Okay, we've talked a lot about magnetic fields here. How do the magnetic fields in the sun vary with time? I'm going to talk a little bit about something called the solar cycle here. And something that's really cool about the solar cycle is it is the longest time series that we have in astronomy. So we know that these sunspots are caused by magnetic fields, and we know that some sunspots are observable on the surface of the sun. So if we just look at how many sunspots there are and where they are on the sun, we can get an idea of what's going on with the magnetic fields. And people have been doing this since the 1500s. A man named Fabricius was one of the first men to record the presence of sunspots. There are also potentially observations of sunspots going back to Chinese astronomers. There are some Chinese astronomers who reported that there was bat-like clouds moving across the sun, which is thought now to have been observations of sunspots. Back then, they had to look on a cloudy day when there was enough haziness in the sky that the sun was slightly obscured and wouldn't blind them as they looked at it. To get consistent observations of sunspots, we had to wait until about 1880. But yeah, some of these cycles go back, to the 1500s. We've got 600 years of observation. But what do we actually see here? So let's talk about this plot a little bit. So this bottom plot here is just how big sunspots are. So you can think of an increase on this y-axis as just there being more sunspots. And we can see that there's a very uniform pattern here in the frequency of the sunspots. And it's actually every 11 years that these sunspots peak and then fall. And what we've got here are some observations of the solar surface. And we can see that this one here in 1996 is a lot dimmer than this one here in 2001. But then 2006, 2007, it's dim again. And if we look on this plot, here is your 1996. Here's your 2001. Here is your kind of 2006, 2007. It coincides with the minima and the maxima of this graph. And again, through up to 2020, this last image here is 2017, as it's getting dim again. And we've got brightness here at about 2014, around here. And these are the solar cycle. That's what we call this increase and decrease in sunspot activity, which is also the same thing as an increase and decrease in magnetic field strength. And what this top plot is showing us is where on the sun these sunspots are forming. So 1 and -1 here are the kind of north and south pole respectively of the sun. 0 is the equator, and we can see that these sunspots form at mid latitudes, and then the formation region of them comes towards the equator before it then stops. The sunspots die off at your solar minimum, and then as you increase again, they start forming again towards the mid latitudes. So yeah, it looks like an 11-year cycle. And this diagram here is called a butterfly diagram because of the way that it looks like butterflies in flight. But what about the polarity of these magnetic fields? Magnets have a north and a south pole. Is that the same for the sun every year? If we look at this version of the plot, where yellow is, let's say, north and blue is south, we can see that actually our north pole is predominant here in the upper hemisphere of the sun, but then it's predominant in the southern hemisphere of the sun for the next cycle. So it's not an 11-year cycle, it's a 22-year cycle, because the poles of the sun, the magnetic poles, flip every cycle. It's very regular. And this solar maximum coincides with periods of strong solar activity. This flipping of the magnetic field that happens every 11 years has happened for Earth as well. In the last 20 million years, Earth's magnetic field has flipped around 100 times. And some planetary scientists think we're overdue another flip. The last magnetic field flip on Earth was 770,000 years ago. There was an excursion 40,000 years ago, which is like half a flip, where it looked like it was going to go and then it didn't. So there are some scientists that think that this could be on the cards soon. It would probably not be great for communication systems if our magnetic fields flipped. I think maybe it would trouble some birds, but yeah, it's not really sure necessarily what that would look like, but there could be one due soon. So possibly understanding more about the solar magnetic fields, the solar cycle, why the poles in the sun are flipping, might tell us more about what would happen if it happened again here on Earth. So we'll move on a little bit now. I've talked about sun-like stars, which have this structure of a radiative region in the middle and a convective envelope around the outside. Stars that are lower mass than the sun, less than about 0.5 to 0.8 of a solar mass, those are fully convective stars. And that's the majority of stars out there, 76% of all the stars. Sun-like stars make up another 23%. And so it's only about 1% of stars that are massive stars, which actually are the other way around. They have a convective core and a radiative envelope around the outside of that. So they've got different structure. You've got slightly different things going on, which control their dynamics. But I'm not going to talk in too much detail about that. So what I'm going to move on to now is talking about stellar evolution. So what happens throughout a star's lifetime? So we've already learned about how nebulas form into main sequence stars. Main sequence means it's burning hydrogen as its primary fuel source. It's in the majority of its lifetime. We've seen that animation from the beginning. So when we are modeling stars and looking at stellar evolution, we know that stars are spheres, but it's difficult to model a continuous sphere. So we simplify it into talking about regions of shells, concentric spherical shells, all around them, all nestled on a central point. And we can see how in any given one of these shells, there's going to be gravity pulling it in, making it contract, and then there's going to be a gas pressure operating outwards, which is causing it to expand. And stars are in, main sequence stars especially, are in hydrostatic equilibrium. They're under contraction, under gravity, but it's balanced exactly by the gas pressure, by this radiation pressure outwards. And so for each of these, for a shell that's closer to the center, both of these forces will be bigger. It's feeling more gravity because it's closer to the center of the star, but it's also closer to the nuclear burning region, so it feels more gas pressure. So you get, for each of these shells, you get a nice balance between the gas and the gravity. And due to a process called negative feedback, these stars are very stable against changes. If you somehow magically reduce the pressure for one of these shells, and so that its gas pressure was less, it would contract under gravity. But if it contracted under gravity, it would heat up, which would cause its gas pressure to increase, the rate of the nuclear burning to increase, and that would produce more gas pressure outwards. And so it would balance that change and it would return to its original state. And this is one of the reasons that stars can stay burning in their main sequence very happily for a very long period of time. Any changes that happen inside the star are then balanced and feed back to themselves to undo their own change. And this hydrostatic equilibrium is an important concept when you're modeling stars. But let's do a simple picture of a star's life cycle. So once it's born, you've got this hydrogen burning shell where your hydrogen burning core, where your nuclear burning is taking place, and then you've got a shell of hydrogen around the outside, this hydrogen envelope. And over time, let's say for the sun, it's got another 5 billion years left on its lifetime of burning its hydrogen into helium in the main sequence. This is by far the longest part of a star's lifetime. But it will eventually burn all of that hydrogen and end up having only helium in its core. It's spent all of its fuel. There's no longer enough hydrogen left in the nuclear burning region. And you've just got this helium left. And the helium is going to be compacted into the central core. The star might not be hot enough to burn this helium. So the helium can't then continue a nuclear reaction. And so the gas pressure reduces and the helium core contracts and gets hotter. Eventually, this core will get to a hot enough temperature that the hydrogen around the core in this hydrogen shell will start burning itself. So we've got an inert helium core, we've got a hydrogen burning shell, and we've got a not burning hydrogen envelope. This hydrogen shell that's burning increases gas pressure on the envelope, which causes the envelope to expand. As the envelope expands, it gets colder. So it becomes a red giant star. So if you're looking at a red giant, this is what's happened. You know that your star has run out of fuel in its core. It's started burning hydrogen in a shell around the core, and it's caused the star to expand. A key thing to keep in mind here, which you'd probably be more familiar than me with this because I don't do a lot of observational stuff, but that for stars, red is cold and blue is hot. This can sometimes be a little confusing, but yeah, so when we're talking about a red giant, that's cooler than a blue star or a yellow star because these bigger stars have cooled down. So once we've got this red giant, at some point, it's going to be keeping on adding helium to the core through this burning in the shell. And at some point, that core will get hot enough and dense enough that all the helium ignites at once in a big explosion called a helium flash, which blows away that envelope, leaving behind a white dwarf. That core of the star is now left behind as a white dwarf. That envelope that gets blown away, this is sometimes known as a planetary nebula. For some time, it was thought that this might be what forms planets, a previous star dying. That's not thought to be true, but that's why it's called a planetary nebula. And you leave behind, this white dwarf star, which will slowly cool and spin down, becoming less and less bright, less and less luminous, until eventually we can't see it at all. It's not giving out any luminous signal. That's for solar-like stars. But what if we start with a star that's much more massive? So we start in the same place. All of our helium, our hydrogen is all turned to helium in our core of our star. Luckily, because we're so massive, we've gotten hot enough that our helium can burn. In this case, we can allow for some process of helium fusing together, which will allow this core to get hotter and hotter, eventually converting into carbon in the center of the core, which results in more gas pressure as the star expands. We're no longer burning hydrogen as our primary fuel source, so we're no longer a main sequence star. These are now becoming red supergiants. They're getting bigger and cooler, but their cores are getting much hotter. This helium is converted into carbon. This keeps happening, and the carbon gets hotter and denser, and eventually the carbon ignites, and that begins to form neon, producing even more outward gas pressure, making our star even bigger. You get the picture here. We can keep doing this. We can keep burning through heavier and heavier elements. Our neon can become oxygen. Our oxygen can become silicon, and our silicon can become iron. And you've got this onion-like structure of different layers of different elements all the way through our star with a hydrogen shell around the outside. Iron, however, doesn't burn. We can't turn that into anything hotter. This is stable, way too stable to ignite. And so suddenly we've run out of fuel. Very suddenly, we've got a massive object, loads of mass. It's very big. And all of a sudden, we've lost that fuel. We've lost our gas pressure. And so our star is going to begin to collapse under its own gravity. As it collapses, it gets really hot and really dense, and it explodes in a massive supernova, which scatters all these heavy elements and creates even heavier metals such as tin, gold, and lead in large quantities. But basically every element that exists is created that is heavier than kind of your iron. That's created through these through supernova and the expulsion of this material. And we're left behind now with just a very hot, very dense core. This is actually so dense that it stops being made of anything at all. It's not hydrogen, it's not helium, it's just neutrons, all densely packed together and held apart by a nuclear force between them, this neutron degeneracy pressure, it's known as. Neutron stars are very small. They can be as small as 24 kilometers across. And if it was 24 kilometers, it would have a mass up to double the sun. They're incredibly dense objects. I think there's a common stat, which is a teaspoon of neutron star weighs as much as the Earth. These are left behind when high mass stars explode. But what if it's a really, really high mass star so that even the neutron degeneracy pressure isn't enough to stop it from contracting even further? And that's how we get this neutron dense core contracting even further under gravity, and it collapses down below its Schwarzschild radius and becomes a black hole. A black hole is just a very dense collection of material that is so dense that even light can't escape its gravity. The escape velocity is higher than the speed of light. So to recap there, our protostars become main sequence stars. For low to intermediate mass stars, these will then become red giants, and then down to white dwarfs, which will then slowly cool and kind of and lose their signature. But if it's a high mass star, that main sequence star will become a red supergiant, which will explode in a supernova into either a neutron star or a black hole. That concludes our kind of recap of stellar life cycles and our discussion of what goes on inside a star like the sun. That brings me to the end of my talk. Thank you very much for listening to me. And if there are any questions, I'll happily take them now. Thank you.
Tom, thank you very much for an absolutely fascinating talk. You filled in some of the shading in my understanding of what's going off in stars, so thank you very much. We're to that point now where it's questions and answers. And as usual, ladies and gentlemen, if you're online and you've got a question, will you put up a digital hand? If you're in the room, will you attract my attention? I will ask my assistant, can't call him beautiful, if he will pass a microphone around for a question. I was thinking about these questions. When you mentioned our sun in these three zones,
I do understand that the density's got to do with the which zone you're talking about. But relatively, what's the density between the core, the radiative zone, and the conductive zone or convective zone?
Sorry, I was just slightly battling with Zoom there. Could you repeat that question for me?
Yeah. In our sun, what are the relative densities between the core, the radiation zone, and the convection zone?
Yeah, great question. I'll bring up a quick figure to slightly answer that question for you. Hold on one moment as I get Zoom ready. Okay, so hopefully you can see this plot here. So this is from a stellar evolution model called the Dalsgaard model of the solar interior, and so we've got radius on the x-axis here from the center of the sun to the surface, and then density is on our y-axis here. And so in the core, it's up here at kind of 1,000 grams per centimeter cubed, more dense than gold. It kind of falls off pretty steadily throughout most of the interior of the sun. It drops below gold, below water, and then you've got this region at the very surface of the sun where it drops off very sharply. This means that when we're doing these simulations of the convection zone, density is very important because there's a lot of change of density in this region that you can kind of ignore if you're doing simulations of the radiative zone because it's pretty steady. Density is quite hard. Density stratification is quite hard to simulate. So we come up with some little approximations and things that make that a little bit easier to ease up on our computing time. But yeah, the density changes very rapidly at the surface. Everywhere else, it's relatively stable change.
Okay, thank you for that. So I'm still looking for questions. In the room, Mike Scollard.
Hi, Tom. You mentioned that the emitted photons were slightly reduced in energy in the radiation zone. What's happening to that spare energy that's not being re-emitted?
Yeah, that's a great question. It kind of is absorbed by the photons, giving them a little bit more energy. As I say, I focus more on the convection zone. I think this is what leads to the temperature of that region. So we know it's a little cooler than the core, but it's hotter than the convection zone. And so the sorry, I'm getting an echo through. It's just losing my train of thought a little. But yeah, that temperature in that region comes from the energy that the individual protons in that area have. So the reason it's hotter than the convection zone is because the protons have more energy. And that comes from the photons as they're absorbed by the protons.
Okay, Mike. Yep. And Kevin Taylor online.
Thank you very much. Great talk, Tom. Thank you very much. A couple of junior school questions. What is it that makes the largest stars burn faster? They have a shorter life, don't they, than our sun? And secondly, I'm really struggling to understand the rate of spin of stars. How they start to spin initially, they speed up, they slow down. Neutron stars go exceptionally fast, and so on. It's a closed book, I'm afraid.
Okay, yeah, no problem. I can talk to you about both of those things. So the first question there was about why do high mass stars die quicker, essentially, and this is something I love saying to some of my students when we're talking about stellar evolution, is that if you've got a lot of mass, then they live fast and they die young. So high mass stars they've got de facto more fuel in them. There's more hydrogen there, so you might think they'd live longer. But the key thing is that because they're much denser, they actually get a lot hotter. And because they can get hotter, there's a certain temperature threshold above which they can do a different method. So I talked about the proton-proton chain in that talk, a way of turning hydrogen into helium. There's another method that's called the CNO cycle, which stands for carbon, nitrogen, and oxygen, which is if there's a little bit of these elements in there, carbon, nitrogen, and oxygen, and the temperature is high enough, and for a star like the sun, it's not high enough, it can't do this, but for high mass stars, it can, then these elements can act like a catalyst to access a much more efficient method of burning of hydrogen into helium. And so it needs a little bit of these elements to be there, but they're left over from previous generations of stars, so that they are there, they're in the interstellar medium, they're inside stars. And because high mass stars get hotter, they can burn energy through a different route, which is much more efficient. So they burn through their fuel much faster, they get a lot hotter and a lot brighter. And so, yeah, that's why your high mass stars die quicker. It's because they can access a more efficient method of burning their hydrogen. The second question was about the role of rotation. How do stars rotate? Why do they rotate? Where does that rotation come from? Why are neutron stars so fast? This is to some extent not a solved problem. There are open areas of research into this as well, especially for later objects in a star's evolution. In general, this is a conservation of angular momentum. So you may be familiar with a kind of a schoolroom science experiment where you sit on an office chair and you spin. And if you hold your arms out, you'll spin at one speed. And if you pull them into you, you'll spin a lot faster. And this is because you've reduced your kind of radius in essence, and that's increased your angular momentum through conservation of momentum. As something decreases, if it's already spinning slowly, as it gets smaller, it will spin faster. It will spin up, is what we call it. And when you've got this big initial cloud of dust and gas, there's going to be some element of just ambient rotation, some preferential direction of movement in the local region, which as this massive cloud, it might be very small, but as this massive cloud starts to condense, starts to collapse down, it will spin up, it will conserve that angular momentum, and it will result in the star itself rotating at a certain rate. The stellar differential rotation I talked about, where the equator rotates faster than the poles, that again is something that there are simulations to understand why. It's very common in simulations that should give us something like the sun to get what we call anti-solar rotation, where the poles are faster than the equator. So there's something to do with the heat transport, with the angular momentum transport from convection in the outer region going on there. We know that beneath the convection zone, there's something called the tachocline, which is a region of very strong shear flow. Below that, in the radiative zone, the sun rotates uniformly. So that differential rotation only exists in the surface layers. So some of the ways that these things exist and continue are not quite known. Similarly, with neutron stars, there's a lot of angular momentum transport between the inner convective core of a massive star and the outer rotation region. We know that angular momentum must be transported across that boundary, but it's not fully understood how that happens. So for these later objects, these massive stars are progenitors of things like neutron stars. Understanding that behavior, there's a group at Newcastle that are working on this at the moment, that do simulations of these core convecting massive stars to understand exactly the angular momentum transport. So it's an open research question, but essentially that initial kick of angular momentum comes from your initial cloud of gas and dust.
Okay, Kevin. Thank you for your question. In the room, Tony Morris.
Hi. You spoke about the magnetic field lines coming out of the sun causing a sunspot because that material is cooler. And you actually said cooler on the surface. Is it cooler down the magnetic pipe as well? Or is it just a surface effect?
Yeah, so it is cooler down the pipe. So what happens is the magnetic fields inhibit the convective motions. So instead of getting your nice flow of material, and remembering that it is the material itself that's moving in the convection region, not just heat through conduction or something like this, but your hot material comes up to the surface, cools, and then falls down again. And what you get in a sunspot is you get a strong magnetic field which stops this from happening. The material is all frozen in place. So eventually it will leach off energy. If it's at the surface, it's radiating out photons into space towards Earth, and it's cooling down. The stuff underneath it isn't able to do that. It can't radiate out photons when there's optically thick material above it. Those photons are just reabsorbed into the material. So you'll get through your material in this flux tube, you'd get a temperature gradient that begins to begins to set up as the stuff at your surface radiates out heat faster than anything lower down. So it would be hotter at the bottom of your flux tube than it would be at the top. But it's kind of, you think of the tube as just being different from its surroundings, from the material nearby that's not within the magnetic field.
Okay, Tony. Roy Stewart online.
Hi, Tom. Can you hear me?
I can, yes.
Yeah, it was a fantastic talk. Thank you very much. You mentioned the coronal heating problem and said there's lots of theories. What's the sort of number one outstanding theory, or isn't there one?
Yeah, it's a good question. It's not an area that's that I've spent a lot of time on, so I don't have a great concise answer to you. I know that there's been there's been a lot of work on I think it's I'll have a quick look. There's a lot of stuff through there's kind of two main things that are put forward as being things that might be causing it. There's kind of heating through waves of motion and energy, carrying the energy from the solar interior outwards through this plasma. So you can get waves with magnetic fields, magnetoacoustic waves and alphane waves, which can kind of, through these waves of material, you can carry heat. The other thing is to do with magnetic fields reconnecting. When these magnetic fields kind of burst off from the surface and they form these loops like we talked about, eventually these magnetic fields do reconnect with the kind of general global profile of the magnetic fields. And when they reconnect, they release a lot of energy when they do that as well. So I think that the theory that I'm slightly more taken with is magnetic reconnection, that it's energy released through these reconnection events, recombination events. That's partially because I've worked tangentially on that problem, so I know a little bit more about it, whereas I've not done much work on the wave heating problem, so I don't know it in any detail. But yeah, I think for me, it looks like magnetic fields are going to play a really big part in that driving of hot material upwards and away from the solar surface, which can transport heat outwards into the corona.
Thank you very much. Cheers.
Thank you.
Thank you, Roy. In the room, Mike Scollard.
Talking about the more massive stars, they go through the proton-proton process. They start to collapse. They go into the triple alpha. The difference in wavelengths that has been released by those processes, combined with the reduced density because the stars increased in size, how does that affect the radiation zones and the convection zones?
That's a really good question. I don't have a good answer for you there. It's not a problem I've looked at in detail. There are a lot of I think when we're typically looking at these objects, what we tend to be wanting to understand is the main sequence anyway. So before this kind of collapse has started to happen, for the most part, that's the region that we're interested in because it's the majority of the star's life, and we don't understand them super well necessarily. So I don't have a great answer for you there. Something that is quite cool about the interplay between the two is because you have a convection zone in the core of the massive star. As you run out of material in the core, and this is another reason that they can live, that they can burn so much fuel, as they're starting to run out of fuel, because they're convecting, they start to pull in material from the envelope as well, as you get this turnover, so they can access additional hydrogen. When we're interested in the kind of dynamics going on, the interplay between the convection zone and the radiation zone, there's a lot there. There's a lot of interesting stuff, but I don't have a great answer for that question particularly.
Okay.
Yeah.
Hopefully you can hear us again.
Yes.
Hi, Tom. I've got a question, really, the other scale of the size of stars, and talking about, say, the high number M-class dwarfs. Now, a lot of these are very flare active, but I was wondering the ratio of sort of core, radiative zone, convection zone on these sort of really cool small stars. What's happening there?
So the cool thing, something about these very low mass stars is that they are fully convective. The entire interior of the star is convecting. This is possibly partially I could picture this being why they're so flare active, is if they're convecting, then they can be driving a dynamo within the star, which can result in stronger magnetic fields. And if it's happening through the entire interior, then you have a lot of magnetic fields changing on a kind of relatively short time scale, which I could see giving rise to a lot of magnetic activity and a lot of flaring. I don't know that that's what's going on, but it would make some sense to me if something like that was the case. So there's not really radiative regions in these stars. There's always a very small radiative region at the surface, because obviously the star itself needs to radiate out photons for us to be able to see it. And the heat has to escape somehow. But yeah, the low mass stars below about 0.8 of a solar mass, 0.5 to 0.8, are fully convective all the way through their interior.
Okay, I'm looking around for any last questions. Back to Tony Morris in the room. He's only had one question.
So I'm doing well.
Tom, he usually has three. Beware. Over to you, Tony.
Right, so I'm sure in like solar literature or literature stars, I've read something about magnestars, stars with extreme magnetic fields. Can you enlighten us on those, please?
Yeah, so I think that might be a magnetar, which is a neutron star essentially, but it's a neutron star, as you say, with an extremely high magnetic field. So again, in Newcastle, there is a group that working on these that had a paper come out relatively recently in Nature, which possibly is something that you've seen, which was on these magnetars, the formation of these magnetars. It is just a fun name that we give to a neutron star with a very strong magnetic field. There's no intrinsic difference between a magnetar and another neutron star. The reason that they have these very strong magnetic fields is not understood, which is why they're a topic of research. How can these magnetic fields continue to exist? There's a few kind of competing theories as to where these magnetic fields come from, whether they're left over from the massive star and they're kind of baked into the neutron star, or whether they're somehow formed within the neutron star itself, or exacerbated by the neutron star, is not super well known. But yeah, these objects can have magnetic fields of kind of 10 to the 15 Gauss, really massively strong, much stronger even than other neutron stars. So yeah, there's a lot of they're a pretty cool object. That's the target of ongoing research.
I'm looking around. I can't see anybody who's wants to ask a question in the room. There's nobody on online who wants to ask a question. Ladies and gentlemen, will you join with me in giving Tom Joshi-Hartley a big next participant in Astronomical Society? Thank you. Thank you very much, Tom.
Thank you very much for having me. Yeah, it's been a pleasure to speak to you all, and I've enjoyed the questions a lot.